Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, let's get started with Lecture 3. In Lecture 1 this week, we talked about how band bending or surface potential inside a semiconductor produces accumulation, depletion, or inversion charges. In Lecture 2, we talked about how that surface potential in the semiconductor is related to the gate voltage that we use to manipulate the surface potential. Now in Lecture 3, and again in Lecture 4, what we want to do is to actually relate the charge that leads to current flow in a MOSFET to the gate voltage. We'll first of all do it in this lecture with what I call a bulk MOSFET. That is a MOSFET built on a typical silicon wafer where the silicon can be considered to be infinitely thick. In the next lecture, we'll do the same kind of discussion, but for a silicon on insulator MOSFET, a very thin silicon layer that's a structure that is being used more and more these days. So let's dive into things. Just to remind you, we're heading for understanding the current voltage characteristics of a MOSFET. Current is the product of charge times velocity. The charge in the semiconductor, there are two kinds of charges if I apply a positive surface potential. There's a depletion charge and there's a charge due to mobile electrons. Only the mobile charge due to electrons will give me current flow. So we really need to understand how that mobile charge is related to gate voltage. In the previous lecture, we talked about how the total charge is related to gate voltage. Okay, so we need to focus on this mobile charge for this lecture. So let's take a look at our band bending again. Let's assume that we have bent the bands. Maybe we haven't created an inversion layer there, but we're starting to get more and more electrons in the conduction band. This will give us a subthreshold current, or a leakage current. So the total amount of charge per square centimeter is minus Q because electrons are negatively charged. And then I have to integrate the electron density per cubic centimeter into the depth of the semiconductor. So I'll take an integral of n of y dy, and the result of that integral is the sheath carrier density, n sub s in density per square centimeter, and then when I multiply by minus Q, I get the charge in coulombs per square centimeter. Now, this electron density as a function of position is something that's easy to understand. We're in equilibrium, the Fermi levels are flat, there's no current flow. So our relation between the electron density and the Fermi level is the equilibrium one. It just depends on the location of the conduction band edge, and that's varying with electrostatic potential. So the conduction band edge follows the electrostatic potential, and that means I can take this relation, I can subtract the conduction band in the bulk, I can add the conduction band in the bulk, I can recognize the electrostatic potential there, and I can recognize an electron density in the bulk, and it turns out that I can write this electron density as the value in the bulk times e to the q potential as a function of position over kT. So there's a very nice, simple way. The electron density in the bulk is Ni squared over Na. That's what I call N sub B. And then as we pull the bands down and bring the Fermi level closer and closer to the conduction band, or bring the conduction band closer and closer to the Fermi level, actually, the electron density just increases exponentially. Okay. So that's the mobile charge that we're after. Let's take a look at doing that integral. We have to do just a little bit of math here, and we'll see that the final result is easy to understand than we might have even guessed. So we're going to integrate that electron density and get all of the charge per square centimeter. The electron density is the value in the bulk times this exponential factor that depends on the potential as a function of depth into the semiconductor. So if I do that integral, it's easiest to do it if I change variables from position to psi. So I'll multiply by dy d psi and by d psi, and we'll change variables. Remember that electric field is minus the gradient of potential. So what I have here is really minus 1 over the electric field. Now the electric field varies with position, but the electron charge is piled up very close to the surface, so it doesn't vary very much, not over the course of this integral. So if I pull the electric field out from the integral, then I have an easy integral to do. We learned how to do this in freshman calculus. And if you do that integral, this is the result that you will get. The electron density is minus Q times the electron density in the bulk times this exponential factor that depends on the surface potential, which tells me how much things are piling up at the surface, times kT over Q divided by the electric field at the surface. Okay, let's take a look at that again. Again, there's a red box around it because this is kind of important. If I look at this expression, I can rewrite it in another way. I can recognize that what I have here is just the electron density at the surface of the semiconductor times a minus Q because we're after charge. And what I have in these brackets is something with the units of depth. This is what I'm getting from integrating over depth. kT over Q is volts, electric field is volts per centimeter. I can interpret this as the thickness of the inversion layer. It's just kT over Q divided by the electric field at the surface. Really, it's the distance over which the potential drops by about kT over Q, and the electron density drops to 1 over E of its value. So the total inversion charge per square centimeter is just the charge at the surface times the thickness of the inversion layer. That's what that integral has told us. This is valid either above or below threshold. Below threshold, we only have a small number of electrons, but they're going to give us this small leakage current. Let's look below threshold first and see if we can understand the leakage current a little bit. So we saw in the previous lecture that below threshold, this factor M is just the ratio of the depletion capacitance to the oxide capacitance plus 1. If we think of this simple voltage divider network and use an average value for the depletion capacitance, it really depends on voltage, but we'll just use an average value. Then we can get the expression that we started with up here. That means we can take our expression for inversion charge as a function of surface potential, and we can try now to relate it to the gate voltage. Then we'll be able to understand the leakage current of a MOSFET. So we'll start with the expression that we just derived, and I'll replace the surface potential by the gate voltage divided by M. But I still have this electric field in here. So we're going to have to do a little bit of algebra and see if we can get everything expressed in terms of gate voltage or things that we know. We don't really know the electric field at the surface of the semiconductor. That's inside the device. So we don't want our final answer to be in terms of the electric field at the surface. Well, we go back to our depletion region formula, and we remember that we had a simple relation between the electric field at the surface and the width of the depletion regions and the dielectric constants. So we can take that depletion region formula. Remember, that's valid because we're below threshold for this calculation. And we can recognize that epsilon divided by the width of the depletion region is the depletion capacitance. So I can express it in terms of the depletion capacitance, which is something that I probably know. That means that I remember that this factor M, this voltage divider ratio, depends on the depletion capacitance. So I could solve for that depletion capacitance in terms of that parameter M. And if I do that, I'm going to get the electric field then will be QNA over M minus 1 times C ox. So we've re-expressed the electric field in terms of things that we have more chance of knowing what they are numerically in a MOSFET. Okay, so now let's see if we can complete the calculation. We have this expression for the charge as a function of surface potential. We have a relation between the surface potential and the gate voltage. We have a relation between the electric field and parameters that we think we know, and I'll remind you that the electron density in the bulk is Ni squared over Na. So if we write down our expression and we express the surface potential in terms of the gate voltage, we had what we had before. If we express the electric field in terms of these parameters, we can write the expression like that. And we almost then have the expression in the way that it is formed. Just a little more algebra and then we're there. So if I look at this parameter Ni squared over Na, that looks vaguely familiar. Think about that. What is that? We've seen something like that before. Where we've seen it before is this parameter psi b. That was related to Na over Ni, so the inverse of that. And we remember that when we bend the bands to psi b, that happens at the gate voltage. So the relation between that band bending and the threshold gate voltage is just given by this simple voltage divider expression, which means that I can solve for Ni divided by Na. Actually, what I have is Ni divided by Na squared here. So when I solve for that, I'll get an e to the minus q threshold voltage over 2 kT. So, you might want to go through that derivation carefully. There's nothing magic going on here. It's just a matter of being careful. But when I insert this expression for Ni squared over Na, I'm going to bring the threshold voltage into my final expression. And the final expression that we get for this subthreshold electron density before we really created an inversion layer is this expression. Again, it has a red box around it because we're going to use it many times. The important point is that the subthreshold inversion layer charge increases exponentially with gate voltage above threshold, so Vg minus Vt. So actually we're going to be applying this below threshold, so this is a very small number, and that means we have a small amount of inversion layer charge, or small amount of electron charge. But the important point is that that small amount of charge varies exponentially with gate voltage. Okay, so we now understand the inversion charge below threshold, so we can talk about the subthreshold characteristics of a MOSFET, something that we couldn't do in week 1. Let's go back and have another look at above threshold. Things looked pretty simple there. We just said that above threshold the charge increases linearly with the amount of voltage that we are above threshold, and the slope is related to this oxide capacitance. Okay. Well, the question I'm going to ask is, let's take a closer look at that slope of that line. We'll find that the slope is actually a little bit less than the oxide capacitance, and this is becoming important these days. So we'd like to be careful about that. So to get started on this problem, let me remind you of a couple of definitions. I can define the gate capacitance as the derivative of the charge on the gate metal electrode with respect to the gate voltage, dQm dVg. That's the definition of gate capacitance. If I put a meter on and measure the capacitance, that's what I would be measuring. Now, we have to have overall neutrality. If I put a positive charge on the gate metal, there has to be an equal and opposite negative charge in the semiconductor. If I'm operating well above threshold, most of that charge in the semiconductor, virtually all of it, is inversion charge. I can ignore the depletion charge. So that charge is basically the inversion charge that we're interested in here. Okay, now we can ask ourselves, what is the slope of this line? That's the derivative of minus the inversion charge with respect to the gate voltage. And you can see that minus the inversion charge is just the gate, is just a charge on the gate. So the slope of that line is the gate capacitance, which, as we'll see in a minute, is not necessarily the oxide capacitance. So let's take a look at that again. We'll start with this relation we had between the surface potential and the gate voltage. We'll remember that the charge in the semiconductor is equal and opposite to the charge in the metal. So that if I define the gate capacitance as dq metal dVg, that's the same as d minus charge in the semiconductor dVg. And now all I have to do is to go to the first equation. It's expressed in terms that I'm going to get 1 over the gate capacitance, but I can take the derivative of this equation with respect to minus Qs. That's going to be 1 over the gate voltage. So if you do that derivative, what you'll find is that 1 over the gate capacitance is just this derivative, the gate voltage, the charge on the metal, which is minus charge on the semiconductor. So if I differentiate surface potential, I get the derivative of surface potential with respect to charge in the semiconductor. When I differentiate the second factor, I just get a 1 over Cox. So if I look at that a little bit, capacitance is dq dV. 1 over capacitance is dV dq. What I have here is a dV dq, but the V is the voltage drop in the semiconductor. The Q is the charge in the semiconductor. So I should call that the capacitance of the semiconductor. 1 over the capacitance of the semiconductor. So what we've determined is that 1 over the gate capacitance is 1 over the capacitance of the semiconductor plus 1 over the capacitance of the oxide. So the gate capacitance is the series combination of the capacitance of the insulator and the capacitance of the semiconductor. Now we saw that before in depletion, but now we're talking about strong inversion. It's also true in strong inversion. Okay, red box around that means it's an important result to remember also. So remember, we understand qualitatively, and it's relatively easily to do this numerically as discussed in books like Pierre's reference. This is the charge as a function of surface potential. All right. Capacitance is the derivative of minus Q with respect to psi s. If I take that derivative in the depletion region, that semiconductor capacitance just turns out to be epsilon divided by the width of the depletion region. So in depletion, the semiconductor capacitance is the capacitance of the depletion layer. But I could take that derivative in inversion also. In inversion, the charge increases exponentially with surface potential, so that derivative is going to be much bigger. I'm going to get a much bigger capacitance. I could define that to be epsilon of the semiconductor divided by some thickness. And the thickness I would physically interpret as the thickness of the inversion layer. Since the inversion layer is very thin, these electrons pile up very close to the surface, the semiconductor capacitance in inversion is going to be very, very large. Okay. Now, if I go back to my recap, remember when we did voltage division, if I did this in depletion, then the semiconductor capacitance was a depletion capacitance. We had this factor M, which determined how the voltage divided between these two capacitors. And we found typically that if we apply a gate voltage, most of it gets in and bends the bands of the semiconductor. However, if I do this calculation again in inversion, where this inversion capacitance is very, very big, then this voltage divider ratio is going to be very, very small. And what that's telling us is that above threshold, a change in gate voltage is going to produce a very small change in surface potential. That's why the bands get pinned at 2 psi b, and it gets very, very difficult to bend them even further. Okay, so we're trying to understand the above threshold charge versus gate voltage. We understand that the gate capacitance is the series combination of the semiconductor and oxide capacitances. We have a definition of the semiconductor capacitance. Well above threshold, the charge in the semiconductor is all inversion charge. That means that the slope of the line that we've been trying to determine is just given by 1 over the gate capacitance. I'm going to give it a label of 1 over C inversion. When I refer to C inversion, I'll be referring to the gate capacitance under inversion conditions, and it's going to be the semiconductor capacitance under inversion conditions, which is very big, plus 1 over the oxide capacitance, which is just determined by the thickness of the oxide. So when I put those two together, we're going to find that the inversion capacitance is a little bit less than the oxide capacitance. Now, years ago, when the oxide thickness was big, the oxide capacitance was small, and this oxide term dominated, and the inversion capacitance was so large it just dropped out of the picture. What's happened with technology scaling is that the oxides have gotten thinner and thinner, such that both of these terms have to be considered, and we find now that in modern day devices the inversion capacitance is actually significantly less than the oxide capacitance. And it's something that we have to be careful about, and we will refer to and come back from time to time as we discuss transistors throughout this course. Okay, so bottom line, what have we accomplished so far? We're trying to understand how the inversion layer charge, which gives us the current in a MOSFET, varies with the gate voltage. We've looked at subthreshold conditions, and we derived an expression that tells us that there is charge below threshold, and that charge increases exponentially with the gate to source voltage. We also looked above threshold, and we found that above threshold, the charge increases linearly, but the slope of that line is not the oxide capacitance, it's a little bit less. It's the capacitance of the gate under inversion conditions. Okay, so we have these expressions now. When we're developing the IV characteristics of a MOSFET, we have an expression for the charge below threshold. We have an expression for the charge above threshold. You might ask, is there a continuous expression that goes from one to the other? And the answer is yes. We can do this calculation numerically. But there's also an empirical one that takes a little bit of curve fitting, and we can fit to the numerical results. And we'll talk about that empirical approach when we return to the virtual source model in the last lecture this week. So finally, let's just return to IV characteristics. We're trying to understand transistors. And drain current is charge times velocity. So the drain current is going to be proportional to the inversion charge. So when we look at plots like this on a log scale of drain current versus gate to source voltage, if I look in their subthreshold conditions, the charge is varying exponentially with gate voltage. We've just sorted that all out from MOS Electrostatics. That's why the current varies exponentially with gate voltage below threshold. Above threshold, the charge varies linearly with voltage. And current is charge times velocity, so the current varies linearly with voltage. So we've got a qualitative insight into why the transfer characteristics have this particular shape. We've done all of these calculations for a bulk MOSFET, where the thickness of the silicon is semi-infinite. What I'm going to do in the next lecture is to redo the calculation for a very thin SOI MOSFET. And it'll give us a chance to get familiar with these concepts a little more, but it will also show us how they play out in a structure that is more typical of the ones that people are looking at in technology development these days. So we'll begin that discussion in the next lecture.